Welcome to solverfy.
All right, so problem number 10 wants you to calculate for the properties of if you have a cyclotron with a radius of a meter, to what properties it takes. You want a deuteron to an energy of 12 mega electron volts. So part A is it wants you to figure out what magnetic field is required to accelerate this deuteron to 12 mega electron volts. So to do that, the magnetic field requirements is going to be equal to the maximum kinetic energy particle to attain. So the maximum kinetic energy is given by K is equal to Q squared, the charge of the particle squared, times the magnetic field squared, times the radius of your cyclotron squared, divided by 2 times the mass of your particle you're trying to accelerate. So now we want to know what B is, so we can just solve for B. So we can say B is equal to the square root of 2km over QR. Is if you can multiply both sides by 2m and by q squared r squared, take the square root, and there you go. So now looking at a deuteron is basically just it's a stable isotope of hydrogen, so it's H12, so it has 2 particles in its nucleus, 2 nucleons, a proton and a neutron. And for the sake of the problem, we can say that the mass of the proton is equal to the mass of the neutron, approximately. That the mass of a deuteron is equal to 2 times the mass of a. So now we can plug what we know in here. So B is equal to the square root of 2 times the maximum kinetic energy we want to reach, which is 12 times 10 to the 6th electron volts, so 12 mega electron volts. Then we want to convert this to joules because our mass units, our radius units are all in joules. So 10 to the 6th times 10 to the minus 19 joules per electron volt times 2 times the mass of the proton, which is 1.66 times 10 to the minus 27 kilograms, divided by the charge, which is just based off the charge of a proton, which is 1.60 times 10 to the minus 19 coulombs, times the radius of the ring, which is 1.0 meters. Now, working through all of this, we need to get, so the magnetic field required is equal to 708 Tesla. It's supposed to be a 7, or basically 0.71 Tesla. All right, so now for part B, wants to calculate what's the frequency of the voltage needed, or what frequency is needed for the voltage between the Ds in the cyclotron. So for part B, frequency is given by the charge of the particle times the magnetic field that you're trying to generate, divided by 2 pi times the mass of the particle, which is equal to 1.60 times 10 to the minus 19 coulombs, times the magnetic field, which we figured out right here, 0.7082 Tesla, divided by 2 pi times 2 times 1.66 times 10 to the minus 27 kilograms, which is equal to 5.39 times 10 to the 6th hertz, or 5.4 megahertz. All right, So part C wants to know, so if they set the potential difference between the Ds at an average of 22 kilovolts, how many revolutions will the particle take before exiting? So now first there are two Ds, because your cyclotron looks something like, all right, let's see here, looks something like this. And the particle is accelerating from here, like this, and until it exits. Now, the deuteron, because there's two Ds here, the deuteron is going to be accelerated here, and then here, and then here, and then here. So it's going to be accelerated twice per revolution. So the energy gain is going to be equal to the energy gain per resolution. So the energy gained per revolution through the cyclotron is going to be equal to 2 energy of the field here. So the charge of your particle times the voltage. So, and it will continue to gain energy until it reaches the maximum energy set by the field, which is 12 mega electron volts. So we can say the energy, the total energy is equal to N times, so the number of times it has to pass times the energy gain in the field per pass, 2 times Q times V. So now we can plug in what we have here. So the total energy is going to be 12 times 10 to the 6th electron volts. I'm going to put this in joules because for coulombs here, so the units match. So that's supposed to be an electron volt times 1.6 times 10 to the minus 19 joules per electron volt is equal to N times 2 times the charge, which is 1.60 times 10 to the minus 19 coulombs, times the voltage, which is 22 times 10 to the 3rd volts. All right, so now we can solve for N. So N, total number of revolutions it needs to take, is equal to 12 times 10 to the 6th electron volts times 1.6 times 10 to the minus 19, it's supposed to be 19 joules per electron volt, divided by 2 times 1.6 times 10 to the minus 19 coulombs times 22 times 10 to the 3rd volts. Okay, so you work all this out. You get this is going to be equal to 273 revolutions. Yep. Okay. Now, part D, you to know how much time it takes for the deuteron to go from the start of the cyclotron to the exit. So the amount of time, so for part D, the amount of time, delta T, it takes is just equal to the number of rotations it takes divided by how many times it takes them per second. So the frequency, which we have solved for already in part B, so we've already solved for N and we've already solved for F. So for N in part C is 273 revolutions divided by the frequency, which is 5.4 times 10 to the 6th revolutions per second. It's equal to 5.1 times 10 to the minus 6 seconds, or 5.1 microseconds. Now, for part E, how much time, estimate how far it travels during this time. So for part E, again, let's look at a cyclotron setup. It has these two Ds, like this, a cavity in between where the particle starts, and it starts with a smaller radius like this, and then it makes its way along the path of the Ds until it reaches its maximum, and it exits the cyclotron here. So to simplify this problem of figuring out how far in total this particle has traveled along this path, we can basically just take the average value, the average path length, as the average radius, or we can take an average radius that it travels. So if we take the average radius as, say, half of the radius of the D, so somewhere along here, which is a, kind of an estimation, but it's not an inaccurate estimation. We can state that the distance it travels is going to be the number of times it circles times the circumference that it circles, 2 pi times 1/2, which, since we're saying that the average radius, so we'll say radius, the average radius is equal to 1/2 the radius. So we'll say 1/2 the radius. These 2's cancel. This just gives n pi times the radius, which is going to be equal to 273 revolutions times pi times 1.0 meters, which is equal to 860 meters. So just shy of a kilometer.